All right, well, if you want to get started, I think we've about enough time.
Okay, cool, fantastic. Classic JPL thing. Just meet 5 minutes after you actually said you would. Okay. Hello. Good afternoon. Happy summer. Not so happy quarantine. My name is Thomas, and I was roped into doing a little presentation about some awesome stuff that I've done. I've done a lot of things, and one of the things I did was actually working on a Resistojet reaction control system at my previous company at Momentous. And throughout this little presentation, I will talk about what all these words mean, so don't you worry. And hopefully you will learn something about how to build things, what kind of things they need in space, and also how much you can gain from 589 even though you don't become a robotics engineer. So that's what I'm hoping for, and I hope that it will not take too long. And feel free to ask questions throughout. You can also wait at the end. I think this is being recorded too, so maybe wait until the end. I don't know. That's up for Brian to decide. I cannot see this chat, by the way, because I don't have the chat open right now. So if you have a question, use your voice. Okay, so I'm just going to go right into it. By the way, I guess maybe I should start. That picture, that is me a few months ago where I'm working on the Resistojet reaction control system. It's the thing that I'm about to crush with the tweezers there. Cool, super cool. Okay, people who know me, they know that I am really into table of contents and proper slides. So I have a little table of contents here. So I'll talk a little bit about myself. Then I'll talk about the company that I work for, Momentous. Then I'll talk about the thing that I did for them, which is the Resistojet RCS. And then I'll go a little bit into requirements, what I had to do. And then I hope while I cover this, you'll get thoroughly confused. So then I'll clear some things up. And I'll give you a little bit of space engineering 101. I'll talk about resistojets. I'll talk about propulsion. And I'll talk about reaction control systems. And then I'll quickly go back to the requirements. So what I said before that made sense. And then I'll talk more, then it becomes less technical. I'll talk about my roles and responsibilities, what crazy things I had to do, the approach, which will be kind of over everyone's head, including mine, and then I think what's important is the challenges, some of the trade-offs, and also the lessons learned. So let's get started. A very wise man once told me that whenever you have an accent, you should let people know where that accent's from. So for those who don't know, I was actually born and raised in Hanover in Germany. There's a little stock picture of what Germany looks like. You cannot see my old house from this photo, but you can see some other cool things. Came here as a high schooler, went to CV, graduated in 2010. Here's another picture of me welding, and this is actually welding for the robot. This is also in 2010, I believe. And then after I graduated CV, I went to college. And I have a little roadmap for it. It's not a good roadmap, but I have a roadmap. I went to GCC, Glenda Community College in California. There's another GCC in Glenda, Arizona. Yeah, I know. Went there, didn't get a degree, just took units to transfer out to UC Merced. At UC Merced, I went ahead and got a degree in material science and engineering. I also got a minor in chemistry because I really like chemistry. Who cares? I found out with life that you take minors for your own sake, but once you've graduated, they mean absolutely nothing. They're minor. Haha, sorry. And then I went to UC Davis afterwards, and I got a master's degree in mechanical and aerospace engineering. So you can see, based on what I'm going to talk about and what my education is, that somewhere at UC Merced something happened that made me want to go to space, and it's actually very true. So more backgrounds. I was an intern at Eaton for a while I was at GCC. I color-coded it so you can see what kind of cool things I did while I was in school, where I was in school. I was an intern at the NASA Jet Propulsion Laboratory while I was at UC Merced for one summer, which made me fall in love with space and NASA and all that stuff. So I switched gears at UC Merced, for UC Davis. And then I had another internship there for 2 years at JPL. And then just recently I was working at Momentous, and starting next week, I'll be actually working as an ACS systems engineer for Maxar Technologies. Yay, thanks. I see Brian clapping. And so 589, how was I related to 589? Well, I was a student for 2 years. I was a student mentor while I was a GCC, and I was also like a big boy real mentor while I was at UC Davis / JPL. One quick thing I want to point out is that job at Eaton Aerospace, actually I got because I talked to mentor Mr. Abrams saying, hey, your company is doing things, I like to go and do things for you. And he said, okay, cool, send me a resume and we'll talk. And I was like, that's awesome. But back then I didn't have a resume, so I freaked out and spent 7 hours writing on my first resume. I still use that resume template, but back then it was resume Thomas_1. Now I'm at _49. So my life has just been an iteration of resumes, and it's been lots of fun. So yeah, and then there's a picture of me, fairly good picture of me at JPL. I do have to say now every single picture that's me without a face mask looks weird, but there we go. So that's me. Hello again. And now I'll actually get into more juicy bits, which is Momentous. So Momentous Space is a startup. It's a space-based startup, and they sit in Santa Clara, which is in Northern California, in the Bay Area, and they build orbital transfer vehicles. And you probably wonder what that is. Well, I stole this picture from their website. The spacecraft they are currently working on is called the Big Red spacecraft, and I've been working on that. And I want to, don't read the stuff, doesn't matter. I want to quickly highlight the diagram that is on the left-hand side that will kind of explain what an orbital transfer vehicle is. The idea is that Momentous, which is the pinkish rectangle, will help the customers, which are the purple payloads, to go into space, into the orbit they want. Previously I mean like literally just a year ago or even today, if you want to go to space with the satellite you have built, or rover, or hot air balloon, or potato, whatever you want to launch up there, you go to a launch provider, you get a rocket, and you spend a lot of money to get that rocket, and you go up, and then you're there wherever you want to be in your orbit, because there's special orbits, and so on and so forth. Now that more and more rocket providers exist, and more of them are willing to do ride-share missions, the cost of going to space has gotten really, really, really cheap. But in particular, the ride-share missions, those rockets usually go to one orbit, and it might not be the orbit you want. So the question is, how do you get from that orbit that the ride-share mission brings you for really cheap to the orbit that you actually need to, you know, do your potato science or have your rover land or whatever you want to do in space. And Momentous, so the pink rectangle with your payload, the diamonds, the purple diamonds, will attach to the rocket. They will go up. They go to the ride-share rocket launch provider orbit, and then they will fly to the orbit you want. So they say they're your connecting flight in space. A more technical term that I heard was a orbit transfer vehicle, transfer orbit vehicle, no, OBT, so orbital transfer vehicle, whatever. One of those acronyms, but really it's kind of like a fancy space Uber. It brings you from one orbit to another. So that's what Momentous does. And it's interesting to point out that right now they are going to launch the first spacecraft in December 2020, and they'll be launching more in 2021. And they have a bright future ahead of them, where they're going to keep providing this service to a lot of very small spacecraft who don't have the capability to build these propulsive elements to push themselves around in space. Because as you'll find out, pushing yourself around in space is very, very complicated. So, okay, that's what Momentous does. What did I do for Momentous? I was a propulsion innovation engineer, or PI for short, because PI is cute, doesn't matter. I needed to develop a Resistojet reaction control system for the spacecraft. So a small thrust resistor system, and it's supposed to work for reaction control, and it was also supposed to be the backup thruster of their main thruster. And I designed, built, and tested 4 of these units for the spacecraft. And this is a schematic of the spacecraft. This is what it's supposed to look like. It's basically a little square, and then on each of these corners, that's where the reaction control systems, the RCS, should go. And probably you'll be confused, but that's fine. Just keep holding on to RCS and Resistojet. I'll promise I'll talk about them in just a second. And then what I'll do is I'll confuse you even more. I'll show you some requirements. So in engineering, what you have to do is often enough you have to fulfill requirements. So people who are above your pay grade or who run the show, they'll tell you, hey, we need you to do this and this and this, because actually they won't tell you what you need to do. They will tell you you need to build something that can satisfy these requirements, and it has to meet this, 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 and so on and so forth. And this was what made this task a little easier, because it kind of was from scratch, was that there was a technology, a vaporized technology that we already had in-house, so I just had to like build all around it. And there's some fancy requirements there. And I hope half the people who are listening are completely confused now, because I'm going to start explaining things, and we'll go back to this. So stay put. Oh, look, cool. Wrong slides. Slides are broken. I got to fix this. Hold on. This is awesome. Give me a second. This is what happens when you work on multiple computers. Anyways, so if someone has questions right now, this is a perfect time to ask for questions while I deal with these technical difficulties. This is great. I feel like a real adult now.
I have a question.
Yes, go ahead, Sam.
Have you ever used Google Slides before?
Yes, I have. I do not like them. Thanks, Google coworker.
Yeah, sure. Hey, Thomas, this is Michael Prudhomme. I saw your ISP in the previous slide of a.
Yes. Hey, Michael.
How's it going? Is that a function of power? Because it's a Resistojet-based system, so I was curious.
Yes, it will be. It will be. You're spoiling it for all the kids, but yes, it will be. Hold on. Okay, so I am sharing my screen again, and I share. So what happened yesterday was I was working on my computer, and then I was like, wow, it's getting hot. I want to work on my laptop, and then I moved it over, and then I saved it on Dropbox, but I still had the older version. Okay, cool. That should make sense because I worked on this and this and this and this. Here we go. Okay, so I confused everyone with the things. Specific impulse that Michael just asked about will be proportional to power, but that's spoilers for like literally one slide. First things first that I want to quickly talk about. I threw a bunch of equations here. Honestly, just two of them kind of matter. The principles of space propulsion. Propulsion in space, or moving itself around in space, is a little different than it is on Earth. Because if you want to move on Earth by foot or car or bicycle or Roomba, let's ignore planes for a second. All of these things, what you really do is you push on Earth and Earth pushes back on you. So there's a transfer of momentum, which is this magical physical thing, or also force. If you maybe know Newton's third law. Actually, let's go through all of Newton's law. So the first law of Newton's law says that everything that has acted a force on it will, like everything is in motion, will stay in motion. So unless there's not a force acting on it, so we'd be all floating in space unless there's not a force acting on us. And there is a force acting on us, which is actually Earth pulling us down. So that's the first law. The second law is that a force can be described mathematically as the product of mass and acceleration. Mass is how heavy you are, what you weigh. It's a physical property. The more stuff you have, the more mass it has. And then acceleration. And acceleration is how fast you get per time. I think you guys' physics teacher, Dr. Platt, calls it the rate of change of speed. So like how quick you get over time. But turns out that you can actually rewrite that equation, that it's not just mass times acceleration, but it's actually the time derivative, or like the rate of momentum with respect to time. So that's equation number one. So the more advanced mathematicians will just call it dp dt, but the idea is that it's that mass and velocity, how that changes over time, is a way to express the force. And usually in all our applications, mass stays the same, so the velocity is different. That's why you just talk to the acceleration, so on and so forth. And the third law, which is really important, that's the one I really care for here, is that for every force that you act on the body or that gets acted on, there's a force that goes in opposite direction with equal magnitude. That's Newton's third law, and this action reaction, and it's often also used kind of like, metaphorically, be like, oh yeah, he reacted to this, they reacted to that, blah, 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 doesn't matter. This action reaction thing is really critical to move around in space, because here on Earth, when When I walk, I step on Earth, I push Earth, Earth pushes me, I go back and forth and all that stuff. In space, there is no Earth that I can directly push on, or body, or what have you. So you bring the stuff you push on yourself. That's where propulsion gets tricky, and that's why in space propulsion you actually talk about the mass changing over time, because you shoot out mass out of your thruster, out of your nozzle, and the propellant, the mass that you shoot out of this nozzle pushes in one direction, which pushes your spacecraft in the other direction. That's all I wanted you to really know about propulsion. You take your own stuff and you push in one direction and the other. And there are like all these like derivations and equations and so I'm going to put them there for people who like math, and I try to explain them. The important one here is the force. It's the thrust is equation 2, which is the force that we talk about when we expel things out of our thruster. And that's a force. The more thrust you have, the more oomph you get out. And it's a function of the exhaust velocity, so how fast your little particles go out. And then dmp/dt, so that's again fancy derivative speak, but for those who have not taken calculus, it's just mass over time. And the mass is the propellant mass. So again, the stuff that I bring with me that goes through. So if I spit out a lot of mass over time, I will get a lot of thrust. And if my particles go really, really fast, I will also get a lot of thrust. Ideally, you want to have both of those work that way. The minus there just shows that it's a directional, that the velocity, if the velocity of the particles goes one way, the thrust goes the other way. And I'm using my fingers to show this because I'm looking at myself. If you guys don't see me, then you might get a little more confused. I don't know if the fingers help, but so anyways, so the thrust equation is kind of important because thrust is just to like show how much oomph you have. And then the other one all the way that I want to highlight here is the ISP, which is the specific impulse that is used as a way to kind of gauge your fuel efficiency, kind of. That's the wrong way of putting it. Anyone who knows anything about space propulsion will probably kill me because I said that. It's really a measure of how much thrust you get out per material you spit out. And there's different ways of describing this. This simple one here is just saying, okay, look at the exhaust velocity of your particles and then divide that by g, the acceleration due to gravity on Earth. So that's like 9.8 meters squared. And then it'll tell you how effective your thrust is, or how fuel efficient it really is in a sense. And the higher the better. So people like to talk about high ISP. It's a slightly more sophisticated way to talk about like, oh, that's a good engine. It's not all just ISP, but in my particular case, I'll just talk about thrust and ISP, because now I'll talk about a little bit about what actually a Resistojet is. Oh, a fun fact that I learned just very recently. It's completely useless, but probably the only thing you'll remember. Pi squared is about g. Yeah, so pi times pi is about 9.8 meters per second squared. I know it's a worthless fact, but when you're in doubt and you need to calculate things, just pi squared. Okay, it's a little bit more serious. Okay, glad the website, this page works. Okay, Resistojet. What is a Resistojet? A Resistojet is a form of propulsion. There are a lot of different types of propulsion methods, but a Resistojet is a type of electric propulsion, and on paper, it's the simplest form. What you do is you take electrical power, so literally out of your wall, and you convert it into thermal power, and that thermal power you use to heat up your propellant, and then you just shoot your propellant out of a nozzle. So basically, you get a heater, a wall heater, or any heater, and then you heat up your propellant, and then you let your propellant go through a nozzle, and you got a thruster. Sounds so easy, right? Why aren't we all doing this? This is marvelous. This is fantastic. Here, I threw a bunch of equations on the board, on the slides, just to sound sophisticated. There's an expression for the electric power that you want to convert into thermal power. The electric power is just the current and the voltage, and that's just if you were to do this at home, this is what you get out of the wall. But when you're in space, these are requirements that the spacecraft would give you that say, well, I can only give you this voltage, so have fun. This is how much power you get out. The thermal power, that you then will need or that you can use to heat up your propellant, and I should say for mementos it's all water, so we heat up water, which again on paper sounds really easy, but oh my gosh, water is difficult to deal with. If you remember your chemistry, when you want to heat up water, there are a few ways where you can calculate the energy required to do it. One is to like calculate how much energy you need to just raise the temperature, which is this MC delta T part. C is the specific heat, which is how much heat you need per material to heat it up, a certain amount of temperature. It has to do with energy. And then here I have M, but I have a little dot on it. Little dot means that it's actually the mass rates. So it's how much mass I deal with per time. Since this is a thruster, we have water coming in and going out, keeps going and going and going. And instead of just looking at total mass, I look at how much mass of water I have per second. So that's mass flow rate. And in fancy calculus talk, they put a little dot on it. Using a lot of notation, that might be confusing. Doesn't matter. There's energy required to heat up your water, and then there's also energy required to change your water from liquid state to vapor state, and that is called the heat of fusion. And there's a little H that denotes that, and that is for water. That's actually a lot. So you will need to put in a lot of heat for your water liquid to turn into gas, into vapor, to boil it. And then there is also like a little bit more energy associated to like heat it up all the way. And then I slapped the thrust equation there just to kind of give an understanding how thrust is actually related to like all this power and so on and so forth. And you can see that this common thread there is this m dot. So the more propellant I have going through, the more thrust I get out. But you know, the amount of power I get to heat it up will also depend on how much current and how much voltage I get. I think Michael asked about how ISP is related to all of this. Yes, no? Michael asked a question again, I forgot.
Oh yeah, no, I was just wondering the relation between ISP generated and power on the Resistojet.
Yeah, it's linear. What happens is the more power you put into your heater, the more electric power you put in your heater, the more power, the more energy you dump into your liquid, which then heats up and becomes gas and so on and so forth. And that will then also overall actually increase the energy that your material has, your gas. And then therefore you'll get a higher ISP, because out of the same mass, you can get more oomph out of it. You get more thrust out of it because you dump more energy into it. So it's a direct linear correlation. Okay, that's Resistojet.
Thomas.
Yes.
Quick question on the thermal power equation.
Yes. Yes.
Your first C, I'm guessing, is the specific heat at constant pressure?
Yes.
Or sorry, constant volume? And then the second one?
No, I think it's a constant pressure one. I think it's a constant pressure one.
Well, but the way I'm seeing this is that's the power required for the liquid phase of water, the transition from liquid to vapor, and then the power in the vapor stage. Is that correct?
Yeah. The first term is how much energy you need to heat it up to. Yeah, you're right. It's power. Sorry. How much energy per second you need to heat it up to 100 degrees Celsius or whatever temperature you need to vaporize. Then the second part is how much energy you need for actual vaporization to occur. And then the third part is how much energy you keep putting in to get like really, really high temperatures.
All right, cool. Thank you.
Yeah, okay, awesome. Okay, yeah, I slapped these equations on not to confuse everyone, but just like, so these are some of the things I need to look on. Anyway, so, okay, Resistojet. You put in electric power, you get thermal power, you heat up your propellant, and you just spit it out and you get thrust. It looks pretty simple. That's why I wanted to do it. But now you're like, okay, Thomas, cool, but what has that to do with this reaction control system? I'm really confused. I don't know what's going on. Great. Reaction control or attitude control is the idea that you can control the orientation or the attitude of a spacecraft with respect to an internal frame of reference. Because again, you kind of float in space and it's difficult to move. It is very, very important for you to be able to know where your spacecraft is at all times, orient it at all times, and then be able to do it accordingly. So here's a little picture that I have of the Soyuz capsule which is one of the Russian spacecraft, and they're some of the things they use to rotate it. So they have like determined the like 3 axes, and then also like a few sensors and how to figure out where they are. So attitude control requires sensors, so you can measure the attitude, which is again the orientation. Actuators, which I hope you all guys know what actuators are, because it's a very, very important word in 589. To apply torque, to move your spacecraft, to change the attitude, and then also algorithms to command the actuators based on sensor measurements or other specifications. So you can see you have a lot of like different branches of engineering going in there, just so your little rectangle points in the right way. And for Momentus, that's in particular important, because if they want to deliver some of the payloads, they need to make sure it's in the right direction. Okay, so I talked about propulsion, I talked about Resistojet, now I talked about a little bit of attitude control systems. So now let's put this back together. I built a Resistojet base, so heating and water, RCS reactive control system, little thrusters that will help the spacecraft to orient itself around wherever it has to go. So I basically just made 4 kettles, put them on a corner spacecraft, and make them go so they can move around. The Resistojet design that I worked on was based off of the existing vaporizer technology that they had. So this part that in the equation to like go from water liquid to water gas to vapor, there was already a little part they worked on, which I call vaporizer, because they vaporized the water. And the CTO back then said, Thomas, you know, we got this vaporizer, I think it works pretty well, we can totally make a thrust out of it. And this was my second day at work, so I was like, yeah, sure, what could possibly go wrong? I will tell you everything that went wrong. And I will go into these requirements again that I remembered. So these are the things that the CEO, the CTO, and the chief engineer, all these important people told me, you know, they said like, okay, we're going to space, everything that has mass costs, so we want to be as lightweight as possible. They said, okay, shouldn't weigh that much. They gave me a number of the thrusts. They said, okay, I want you to be able to like push at a certain thrust level in this direction, which again is just a force. And then they also talked about the specific impulse, which is kind of like the fuel efficiency, because they don't want me to like use gallons and gallons of water just to like do one little, thrust interaction. And that's the thrust they wanted me to reach, which is measured in seconds. Then there's also this thing called the minimum impulse bit, which is a little bit of a profile of what your thrust over time looks like. And they wanted it to be this particular shape, doesn't matter. The other important one is the power consumption. So they said, look, your P equals IV, your electric power is only 25 watts. Have fun, make it happen, which was actually really tough. And then there's another one that's important for space plumbing or propulsion systems, is the inlet pressure. So at how much pressure we would get the water to come in. 250 to 350 kilopascals is not a lot. For those who don't know any of these units, 100 kilopascal is the bar, which is 1 atmosphere, which is 14.7 psi. So if you know psi, then 3.5 times atmospheric pressure is 3.5 times 14.7 psi, which is like 45 to 60, something between that. Let's call 50 psi. If you know what 50 psi are, great. I learned that people have preferences when it comes to units, when it comes to pressure. So whatever. So they gave me all these requirements. They actually gave me more, but I put this slide together after I parted with Momentus, so I didn't have access to my files anymore. I was just thinking like, which of the requirements were like the worst that I had to deal with. So yeah, these are the ones. Okay, cool. So I hope I can get you all back. I promise everything else will be less confusing now. Okay, great. Let me quickly talk about my roles and responsibilities. I should point out here, I'm recycling these slides. I used these slides previously for a job interview, so we're like, oh yeah, tell us your most impressive and most awesome thing. And they kind of also want to know what I've done. I've done a lot. If you think of 589, how it's split into different groups, where you have the fabrication team, and you have the CAD team, and you have the people who work on driving and electronics and all that stuff. Real companies and real projects will have this division too. Momentus was a small company. When I joined, I was like the 25th employee, and when I left, I was 60th or something like that. So I was wearing a lot of hats. I was doing a lot of analysis. And analysis means just calculating things on paper or using the computer, using Excel or MATLAB or other tools to just show that we can do the math, and on paper using the math, this crazy idea that we have, which is having a tea kettle in space, pushing my spacecraft around, will work. And I kind of worked on the concept. I worked on the thermal stuff, which thermal was all very important. And also the structural thing, making sure the thing doesn't fall apart. I was also the design engineer, so I spent a good amount of time on CADing and looking at parts and making sure things kind of fit, and then also selecting the right components. It's easy to buy things from like MasterCard or DigiKey and just put them together to make sure it works. Because why invent everything? Why should I build my own heater when I can buy a heater from a reliable source for $20? But you have to find these products, so I need to do that. I was a subsystem engineer or a system engineer. That one is my most favorite title because systems engineer is really a person that does very well in communicating. So talks to all the people in the different components of the thing you built. So for a robot, the system engineer would talk to the fabrication people and the CAD people, making sure they can get along, not personally, but professionally speaking, that the CAD dimensions work out, that the fabrication team can do everything, and that the electronics are meeting all the requirements, the rules of the game, and so on and so forth. In space world, that meant I had to track the budget of mass. I had to make sure that I know how heavy I am. I had to make sure how much power I need, and I had to make sure that my thing will fit onto the spacecraft. Like you just put a few bolts on and it works at all times. So I had to track that too. And it was funny because I was leading a lot of the other teams, so I was talking on behalf of myself to a lot of other people, and on behalf of myself to myself sometimes. Then I was also doing a lot of project manager things. A project manager at 589 is basically what Mrs. Martos does. So make sure you keep the schedule, you keep the cost budget, you have design reviews, you you track risks, and so on and so forth. This is actually what a lot of vendors do, but Mrs. Martos really spearheads and make sure that we're all there. And then I also did, this is also the most robotics part of it actually, assembly, integration, and test, or AINT engineering. So all the stuff that I got, all the components, I tested them, made sure they worked. I put them all together to make this whole little thing. I did qualification testing. So once I built my thing that has technically never been built before, I made sure that it really does what I did all the math as an analyst. And then once I was happy with that, I built more of those and then did acceptance testing just to kind of do check mark to make sure they kind of work. And then I screwed those little things on myself to the spacecraft, which was pretty cool. And then a lot of these things I have done myself, but I had a lot of help with all these people, with all other people at Momentus. In particular, the person who helped me a lot, his name was Calvin, who was an intern. And he did a lot of the work when it comes to mechanical design. I was there helping out and this and that, but he did a lot of work himself. And I think it was fun for me, who was an intern for so long, to work with another intern and give him. And I guess the moral of the story here is really, interns do get to do real things. Don't think they don't. If you happen to be in a situation where you're an intern and you don't get to do cool things, talk to people. I'm pretty sure that'll make you do cool things. Worst case, talk to me. I'll make you do cool things. Okay, so I did a lot for that. I just want to quickly point that out. Now I'm going to lose you again for a few seconds. I'm going to talk about how I did it. And here I'm just going to kind of skim the thing. But I basically made a fancy space kettle. The idea was that I will have 3 water channels, because in each corner I will put 3 nozzles, 3 thrusters that will point in an X, Y, and Z direction with respect to the spacecraft, not respect to Earth. And I will have them be able to shoot out water at every given moment. So in this diagram here, I color-coded it, but it's not colorblind friendly. I'm sorry about that. The top half is this blue part where the fluidics assemblies, where I have little valves. So water comes in from the spacecraft, and I have valves that open and close according to when I need the downward channel or the downstream channel to operate. And I got some fittings and all that stuff to put it together. And then I have my thruster assembly, which was a big old copper block with nozzles and heaters inside. so that the water would go through this copper block that it heat up. That's why we use copper. Heat up all the way with like these cartridge heaters that you can buy, literally just $20 on. I think you can get them from McMaster too. You heat up this copper block to a stupid high temperature. The water goes through that copper block, heats also up to a stupid high temperature, or to be exact, to go back to Sam Linker's question, it heats up until it vaporizes, and it keeps heating up to a ridiculous temperature, and then it gets shot out through the nozzle. And all you need to do, the idea is really just turn on the valve, so water goes through, and it keeps going out and out and out, and then gets really heated up and leaves its steam, and then it gives you a little psh in the different directions. That's kind of what the system was supposed to do. Another things that are fun to mention, we wanted to heat up the water to 500 degrees Celsius. I do not know how many Fahrenheit that is. It's a lot of Fahrenheit. It's about 9/5 times 500 plus 32 Fahrenheit. I don't know, like 1,000. You have calculators. You guys are geniuses. You can probably do this math in your head. I don't. Quite frankly, this is a weird thing to say. I don't care how many Fahrenheit it is. Let's see. What else do I want to talk about that? Well, let me go to this picture. This is actually what it looked like. Before you like gasp and say anything, I asked at Momentous. I specifically got these pictures cleared. They're open public. Everybody can look at them. This is great. This is what the unit looked like. And I will look. I'm going to start annotating. I'm going to take it apart a little bit here. I have a little bit of mic. So what you can see. This is. Yeah, I'm looking at this picture. I'm looking at the back picture. The water comes in from the top. You can see a lot of like crazy wiring because I have heaters in it and sensors and all that stuff. And there's this little plastic part that splits the water into 3 channels, and that's simple. The valves are hidden in this aluminum block. And the reason why that is because we're worried that these valves are kind of picky. They're beautiful and amazing, but they're kind of picky. They can operate only at a certain temperature. So we want them to make sure that they're always warm and cozy and yet cold enough, that they don't get too hot or too cold. There's a little heater there that in case they get too cold, I could turn it on. There's also a little sensor there where you can't see. These are the valves here. And then they keep going into these fittings where I screwed one part of the valve with this little tubey part here that I'm like highlighting now. And it has a lot of loops because these are capillaries. And capillaries are tubes with a very, very, very small inner diameter that you use to actually reduce the pressure. You get quite a pressure drop out of it. And that is because one of the requirements that I had before, the inlet pressure that I got was, again, this like 60 PSI or something like that. That was too high for me to get the thrust that I wanted. So I did the math and I did the analysis and looked at like what kind of pressure I want and realized, well, this pressure is too high. I need to do something. So you use these capillaries to get like massive pressure drop out because how much pressure you lose is proportional to the inner diameter of any tube, to the 4th power actually. So if you like cut it down by a factor of 2, then your pressure goes down by a factor of 2 to the 4th, which is 2, 4, 8, 16. 16, that's not 16, that's 4. 16, so that's pretty massive. And then the reason we have to do the loop-de-doops is because we did the math and we needed 4-inch capillaries, but we only had like 1.7 inches of like real physical space. So we're like, well, we're just gonna loop it. It's not the most elegant solution, but sometimes engineering is like that. And then, so it goes through the water, it goes through capillaries, the water goes through capillaries after it leaves the valves. And then what you can't see here, but I'll show it in the left picture, this little block here is my copper block. Now you're gonna be like, Thomas, you said copper, this is not copper colored, this is silvery. It's because we coated them with nickel. So I call these blocks actually a little bit like Iron Man because Iron Man is not iron colored. He wears like gold, titanium, whatever's here. Copper is a beautiful material, has great thermal properties, but it oxidizes, and it oxidizes to copper oxide. And copper oxide is not with good thermal properties. So the best thing you can do is to just coat it. So we coated it with nickel, so it looks like nickel-y and silvery on the outside. But this is the block, and you can see the water goes in there, and then the nozzles are still made out of copper, and they have currently fancy tape on them so that they don't get clogged up to keep them safe. This is what the system looked like. This is what I was able to put together in a while. The other thing I want to point out is this fancy silver shiny thing is just aluminum. These are my aluminum structures. Other things made of aluminum. But this here that I'm like turning red now, I'm getting crazy with my annotations. This is titanium. So I used actually titanium to hold my really, really, really hot block. And the reason why I use titanium is actually to not lose all the heat from that copper block back to space or to the spacecraft. There's how do I want to say this? So, okay, there's this field of study in engineering and science in the world that's called heat transfer. And heat transfer is talking about how you lose heat, transfer heat to everything else. You can imagine, because you've probably done this in the real world, if I heat something up really, really hot, you can feel how hot it is by just kind of putting your hand around it. That's one method of heat transfer, which is called the radiative heat transfer. And then another one is the conductive heat transfer, where I touch like ice cream and it's really, really cold. But what's happening is actually I am transferring heat from my finger to the ice cream and the ice cream starts melting. Or the other way around, in this case, my hot block touches the spacecraft and the spacecraft gets really hot. But I want to minimize the spacecraft getting hot because I don't want to lose all this heat that I'm carefully putting into my block to the spacecraft, to the little corner. So I use titanium as structural supports because it still needs to be held, but titanium has very low thermal conductivity, which is a measure of how well it can conduct. So transfer heat through touch, through conduction. And yeah, so aluminum has low thermal conductivity. Oh, sorry. Titanium has low thermal conductivity. That's why I use titanium for all that stuff. And I use aluminum for everything else because aluminum is actually pretty high. And I wanted to make sure that all the other things on top actually kind of stay still cold. So let me see. Is that all I wanted to talk about? Oh, okay. And then there's also this here. I'm going to use one more color just to make everything worse. I'm going to use blue. This little part here that you can't see in the other picture, that's a radiation shield that I put on top of the RCS units, again, to mitigate a radiative heat loss, because I don't want to lose all that energy that I put into block. Okay, so that was kind of complicated. But yeah, I basically just made a space kettle that is copper-based, put a bunch of heaters in, call it dunsies. A lot of colors. Made sure that I don't lose heat, and it's powered. Okay, I'm going to clear all the annotations. There we go. Okay, I'm gonna close this. Ooh, no, not done. Here. Okay, some of the challenges. This might be a little bit interesting. So I made this look so easy. I've been talking for, oh crap, I'm running out of time. I've been talking for so long. I made this look fairly easy. What were the challenges? I'm gonna go a little faster now. Challenges were finding the right components. 500 degrees Celsius is a stupid high temperature. It's really difficult to just buy regular things with McMaster cars saying, oh, will this withstand 500 degrees Celsius? Cool, great. Metal stew, not many. Well, actually a lot. Not all of them. But plastic is difficult. So actually the 500 degrees Celsius threshold was really, really bad. The nozzle design, so the little nozzles when my water comes out, took a little picture here of what a Bell nozzle design usually looks like, was difficult too. Because I did some analysis and I got a design for a nozzle that looked different than many other nozzles. And then a lot of more established people, including my CTO, were like, well, it shouldn't look like this. It sounds wrong. So should I trust the math that I did? Should I trust the people who have a lot of experience? Should I test it? The idea is we wanted to test it. We got all the nozzles, but then we never got to test. So I was like, you know what? I'm going to make my superiors happy, which is a decision I made. I don't know if it's the right decision or a good decision, but it's a decision I made. Didn't get me in trouble, so I guess that's a good decision, actually. And then the other thing is vaporize internals. So the part where we actually vaporize, it's not just like an empty channel. We put a lot of other things in there, which is kind of proprietary, not really. I don't really remember. But yeah, these things clog my nozzle like crazy. What the heck? You know, I'm trying to have this like optimize my heat transfer, but it didn't work out that well. So I had issues with those. Heat transfer itself was complicated. I spent a lot of time talking about, but it's difficult to like get something really high temperature to low power. It's actually really hard to do this on Earth too, to test it, because there's a lot of air and stuff like that. And then also talk about the thrust performance. It was really hard to get the same level of oomph all the time. There were some instabilities. Turns out that over time, as I keep like spitting out water, it like goes down in a sense. So things were not easy. They really aren't, but it's okay. kind of overcame them. Some risks and trade-offs. These are really fun. In engineering, you always have to talk about risks, like, you know, when you build something, like, oh, how risky is it, and so on and so forth. Which one do I want to highlight? Yeah, the oxidation. So the second point, erosion and oxidation of the copper block. That was a high risk because copper is great, but copper oxide is complete garbage, and I don't want it for the purpose that I use it for. So, you know, that was a risk we had to mitigate, and we're like thinking about it. And someone said, "Can we just coat it?" And I was like, "Yeah, let's coat it." First, we wanted to coat it with gold, which would have been great. But then we ran out of time. Surprisingly, gold coating is not that expensive. Something to think about, 589. Gold coat your stuff. It looks cool. But we went with nickel, so that went really well. The other thing we're struggling was also some of the heaters and the resistive temperature measuring devices that I got. They had a really long lead time. So lead time means how long it takes for you to get your stuff after you order it. They initially said 16 weeks, but then turned out to be like 40. Momentous works really fast. So 40 weeks was basically like 5 years from now. It was ridiculous. So it was really tough. And then we also had to do some trade-offs. Trade-offs is where you kind of look at trying to understand, trying to like figure out what kind of thing you want to use. You know, should I choose A or should I choose B or C? You do a trade-off. You figure out what are the pros and cons. The manifold, the copper block material we were looking at, like, should we use copper? Because copper erodes, it's kind of lame. Can we use something else? High temperature, blah, blah, blah. Again, looking at the nozzle, so to change that. And then also, you know, do we want to like put in only a little electrical power and save the whole system, the whole spacecraft power, or do we want to get a lot of info? So there were some trade-offs we looked at, and we came to a conclusion. It was all great, marvelous. Oh, look, I'm almost done. That's fantastic. I want to share some lessons learned with you. The first one I think is very important for 589. I did a lot of design that did not keep manufacturability in mind. So I designed something that looked great on paper, but then when it came to me building it, because I had to build all this stuff, I was like, wow, who was that shabby designer? Who gave me this stupid thing to put together? It was I. I did this to myself. So whenever you design something, think that you have to put it together. And if not, then someone else has to put it together. And don't be mean, you know, respect everyone else. So do it easy, or just think about things. And I understand it's not easy to design with manufacturability in hand, but ask for help. Ask for people who know how to machine things. Ask people who have experience with this. You know, make sure to ask other people. Ask me, for crying out loud. I know now a little better how to do that. Testing is important. I think Mentor Molly says this at least 5 times every single 589 session. It really matters. Not just to make sure that your thing works, not just to make sure that you can prove to yourself and everyone that you know what you're doing, but also sometimes when you don't know what you're doing and you want to settle a little dispute by should I have big nozzles or small nozzles, you build them, you test them, and you can say, aha, it doesn't matter at all. Aha, these nozzles work. Aha, hey, turns out I totally forgot to like do something else. You learn a lot about testing. Vaporization is difficult. I learned that actually boiling water is probably the hardest things we ever do as humans without really thinking about it. There's so much I can tell you about vaporization, how people get PhD theses on it. If you don't have to boil water other than making yourself coffee or tea, I highly discourage you from boiling, ever. And then the other thing that's like a light, cute little thing, tea time is problem-solving time. So as my first role as kind of like project manager and talking to people, I decided that every twice a week, Tuesdays and Thursdays at 3 p.m., I would have tea time where the whole team, which was me, the intern, and then occasionally 2 other people, would come together and would quickly, for half an hour, talk about some challenges that we're facing in that day. And a lot of these challenges were supposed to be about this Resistojet, about this RCS, but often enough it wasn't. You know, with some other problems going on in the company, or people saying, hey man, I'm trying to get this done, but like your stupid CAD software doesn't work, and then someone says, oh, I have this problem too, here, just click this, click that, and so on and so forth. With a small team, which 589 is kind of small, but especially subsystems are really small, it's really great to come together often and just quickly have a few minutes of like discussing some of the issues you have. Even if you just chit-chatting and saying, hey man, my English homework was really tough, I don't know what's going on in Frankenstein or whatever. Yeah, I think that's it. That's it. So I talked way more than I wanted to. Please stay on and tell me any questions you might have. But in the meantime, thanks for your patience and listening to my rambling. Okay, I'm gonna stop sharing. Everybody's muted. It's kind of scary.
Does anyone have any
Thomas, you
questions?
did so well.
Oh, thanks, Molly.
I have a sort of a small question. You talked a little bit about some challenges that you had during the project. Can you go into specifics, like how you overcame some of those? Like what did you actually do when, oh no, the nozzle wasn't working, or whatever?
Yeah, that's a great question. When you encounter a challenge, or a lot of the challenges that I encountered is you put something together and you're like, oh no, this doesn't fit. Oh no, this doesn't fit. You just literally just stumble upon the problem. Since they were all really, really urgent and almost life-threatening to the project, the first thing I did was relax, make a cup of tea, take it slow, don't panic. Sometimes a little panicking was involved too, but just relax and approach it. I would talk to a lot of other people at the company who had a little bit more experience, who saw something like that. But then I would also often enough just do some research, or just use my own previous experience and knowledge as you think how to overcome that. So for example, when things were not fitting, when I bought things from 2 different vendors and they were actually not fitting, instead of saying, oh no, this is over, I can't get my nozzles in, we're not going to space. I decided, well, I'm pretty sure if you shave up a little bit here and there, like you just make it fit. So I went to the machinist that I had to saying, hey, stuff doesn't fit. What can we do? And he said, we can do this and this. And I was like, all right, cool. And then I talked to, my supervisor and said, hey, stuff doesn't fit. I want you to do this and this. And he said, yeah, that sounds good. There was a little bit of process of whenever you want to make a change, ask people, come up with an idea. I don't know if that kind of answered your question. It was more anecdotal for like one thing, but usually just think about it, ask for advice, and then just tackle the challenge face head on. Just deal with it.
That totally answers the question. I guess since I work on very different kinds of problems, like I know how I go about debugging things, but like if I was in your situation and like something stopped working, I would have no clue what to do.
And sometimes it's also as easy as like opening the book. Sometimes I was like, hey, look, I did the math and it says I need like 5 billion gigawatts to heat up like a speck of water. And I was like, that shouldn't be that way. And then I opened the book, it's like, oh, look, I forgot a minus in my equation. Yeah. Okay, awesome question.
I have a question for you, Thomas.
Yes, go ahead, Tanner.
What lessons do you think you took from 589 when you were a youngster that you currently use in your day-to-day life today?
Oh man, that's such a great question, and I want to incorporate it in the slides, but I didn't. I think really the biggest thing I learned from 589 was actually communication. You'd be surprised how important communication is in engineering, and the ability to communicate to yourself, aka writing things down, really helped me a lot to keep 2 weeks ago Thomas up to date with current Thomas, so that I know what's going on. These things were also then important to help, for example, new hires that would come into my assistant and help me for a little bit, understanding what the frick is going on. I could be like, hey, here, look at this document that I wrote. This kind of explains things. And then we'd go over it and be like, wow, I know way more about this now. Communication with other people would also be helpful to, establish what you need to get your work done, and also let people know what you have done as well. So in particular, also presentations, a lot of like fancy design reviews you have done. I think I've learned a lot about public speaking and technical speaking, so talking about engineering things in front of others, so that when I had these very important design milestones, these presentations, people didn't really have any issues with what I said. They said, okay, you said A, B, and C, and that makes sense, and we can do it. So I think that one was really important for 589. Also, I guess having fun. Building robots was fun, and building a Resistojet reaction control system, while it sounds more complicated, was just the same amount of fun. Yeah, so communication and fun.
Hey, Thomas.
Hey, Molly.
Hey. You said that you're starting at Maxar soon, right?
Yes, that's right.
Are you going to be doing the same propulsion-y things there?
Kinda. My title is ACS Systems Engineer. ACS stands for Attitude Control Systems. So that slide that I talked about attitude control systems is stuff that I just recently learned myself because I'll be working on that. So I'm really excited about it. A good chunk of that information will be needed. Yes, learning about propulsion stuff and so on and so forth, but it will also go into learning what kind of sensors there is that your spacecraft knows where it is with respect to the thing that you care for, you know, where it is with respect to Earth, respect to other satellites, with respect to, I don't know, maybe the moon, maybe the ISS, and algorithms and all that stuff. So yeah, some of the knowledge that I have will be useful, but I think there will be a lot of new stuff, and I'm equally frightened and excited. So it's gonna be fun. Any other questions? They don't have to be about this presentation. You can ask me about my time at GCC, which was okay. It was not the best, but definitely wasn't the worst. I do recommend it though.
Ooh, actually, I have a question.
No, go for it, Brian.
All right. For any 589ers who might be here or will see this later, who are going off to college, do you have any tips for them?
Hydrate, sleep. I'm pretty sure I only made it for college because I decided to go to bed. No all-nighters. I didn't have the best GPA, but I had a pretty good one, so sleep. Be curious. Never be afraid to do something new. Something new in college can be signing up for a class that you don't even know what the word means, that like it says. I actually have done that. I took anthropology that way. I didn't know what anthropology meant. Maybe research a little bit ahead of time, but still, anthropology was great. Be willing to sit in a class, which is like taking a class, but not really. That's how I took an astrobiology class during a very busy semester. Told the professor, I don't have time to take the class. I really want to learn it. Can I just sit in the back? And he said, yes, you can. Yes, you may. So that was fun. Get engaged, get involved in clubs if you want. I did a bunch of engineering clubs, but I also was part of UC Merced of Taco Club. Tried to find the most delicious taco in the city of Merced. Fun. Do research. I am a little bit more of a research PhD, trying to understand the universe type of person. So I enjoyed a lot of academic research. You know, going in a lab, putting things together, going to meetings where all these like fancy professors talk about stuff where you have no idea what's going on, but just because you sit in the like little meeting, you'll learn so much. Yeah, just try out new things. You know, your major is not going to define you as a person. It's not going to define your career. I mean, I started out as a material scientist because I thought chemistry materials are cool, and they still are, and I'm glad I learned about them. Not doing much materials now, and it's good. It's fine. So yeah, that's pretty broad, I guess. I don't know if that's good advice. Sleeping is definitely the best advice. Go get sleep, but yeah, be curious. Also, congrats to the CV class of 2020. I hope you guys will do great in college. I'm really, really proud and happy and excited for you. And you also guys get lucky because since you don't have a real graduation, which is sad, teardrop, you have all these other super famous people doing commencement speeches, which is really great. Because my commencement speakers of all graduations that I've done, I don't even remember their names, so they were not that important. That's a horrible thing to say. Sorry. Go see.
Hey, Thomas.
Yes. Hey, Michael.
So I have a question. So you mentioned earlier when you're in the design process, you know, if you have sort of an initial concept in mind, you can kind of let the math guide you. But if you are tasked with designing something and you don't know where to start, do you have a process you follow in order to kind of get started, or just, you know, start tackling a problem? Or
yeah, the way I tackle problems in design, in engineering design, is almost everything I've designed, I have kind of seen in a class. When I had to design a thruster, I've taken classes on like, this is what a thruster looks like. These are the principles, blah, blah. This is physics, this is gases, and so on and so forth. So I always knew at least a book to open to kind of get an idea, to be like, these equations describe physical processes in the world that look like what I want to get done. And if I massage the equation a little bit, if I keep reading that chapter, if I maybe open up that Wikipedia article, I got something going. If I were to start a project like that requires technical knowledge and something that I have no idea about, Wikipedia.org/ I don't know, let's start ACS, Attitude Control Systems, and start reading things. If you're in a collaborative and supporting environment like Momentous was, and I hope 589 is, no, I'm pretty sure 589 is, you can ask people like, you know, Mentor Brian, or Mentor Michael, or Mentor Mr. Wilton, or, you know, just ask other people in teams saying, hey man, this is my first time putting two pieces of metal together. What should I do? How do I do this? And then people will say, well, have you cut a hole? And then you might ask, why do you need a hole? This and that, and so forth. So I start with asking people and or researching myself because I want to learn something new out of it too. So that's how I become. Again, I still think that's a really broad answer. I really hope that answered your question.
No, that answers it. It's a broad statement too, but you know, it's a
problem solving is kind of broad. Sometimes you just start it.
Yeah, that's the hardship though. It's, you know, sometimes you just have that blank canvas, and it's not like a school context necessarily where you have some guidance or, you know, a specific problem set. Sometimes it's very open-ended and generic. So
that's true. That's true. And when it gets overwhelming, then you just grab your favorite mug of tea or coffee and hydrate, or caffeinate, I guess, in this case.
There you go. Thank you.
Thomas, so what are the functional differences between ACS and RCS?
That's such a wonderful question. ACS is like attitude control system. So there's a lot of actuators involved in ACS. There are, you know, reaction wheels that have a certain amount of momentum loaded in it, and it can kind of go back to where you want, and you can apply levers and all these other things. I think it is my understanding that RCS, reaction control systems, are really just actuators that provide reactive forces and just kind of keep pushing. To put a little bit of perspective into this, when I started Momentous, I called this ACS the entire time, and then they said RCS the entire time, and now I'm working at something that is called ACS. So I think it's a bit of semantics, and I don't have a good answer. They're kind of the same, but they're not. Okay, Sam Linkhurst is silent because he's not satisfied with that answer, but that's okay. Sorry.
You satisfied the other Sam.
That's good.
All right, we have time for one more question if anyone has anything.
Hey, Thomas?
Hey, Mr. Gustafson, how are you doing?
I'm doing great. I'm going to try a different camera. I don't know if it'll work, but anyway. My question is, did you consider using any propellant other than water? I mean, given that oxidation was such a problem.
Oh, so yes and no. Yes, by looking at it like the first 5 minutes, and then later when we had some other crazy ideas, but mostly no. So the Momentous thing, their main thruster, which is a plasma thruster, which I didn't talk about, they use water as a propellant as well. So the whole company wants to use water. For one, that it's a green propellant, but also like way into the future, they want to go into asteroid mining, and they want to mine water out of the asteroids and use that as a propellant. So they already wanted to start working on technologies that could enable using water. But you're right, water erosion and corrosion and all that stuff is really tricky and quite a pain to deal with. So I was actually looking at maybe for future missions, if we can get like bigger spacecraft and way more power, what if we can electrolytically split the water into just pure hydrogen and pure oxygen, and then use one of those propellants. Now, those propellants have some issues with them as well, and you know, sometimes it was like 3 p.m. in the afternoon, and I was like, oh crap, I have to do all this other work. So yeah, we considered it, but this was more of like a company push to just keep with water, because it was, you know, the one propellant we use, so you don't have to get multiple tanks and multiple other fluidic lines and so on and so forth, make the whole system easier. Didn't make my job easier, but make the overall system easier.
Okay, yeah, that kind of thing happens a lot in engineering. So
that's right. That's right. All right, that was a really good question. Thanks.
All right, cool. So thank you, Thomas, for being our guinea pig on this process. And thank you to everyone who showed up. We hit 30 participants, which is really cool for our first time. Shout out again to all the alumni that came and have agreed to talk in the future. Shout out to our mentors, shout out to the car crew, and the 589ers who actually were able to show up today. And yeah, this was pretty good.
Thanks everyone for listening to me and for having me. I hope you guys learned something.